All right. Thanks a lot, Jerry, and thanks everyone for coming out today to hear what we've got to say about nitrogen rate and timing. So like they said, my name is Chris Bandura, Conservation Outreach Specialist for the state. Really going to focus on N rate and timing, and we're going to look at agronomic, environmental, and economic considerations, kind of all in one subject today. So let's dive in. Where we are going today is we're going to relate the concept of our nitrogen application timing to seasonal precipitation patterns, mainly early season precip, nitrogen cycling, and crop demand. We're going to review a regional, and by regional I mean 8 Midwestern states in the Corn Belt, as well as some Wisconsin-specific N rate and timing studies that can give us some insight as to where one timing strategy might be advantageous over another. And this, yeah, like Jerry mentioned, this is the question we're here to try and answer today. And I'm honored to give the extension answer right off the bat, and I'll tell you it depends. So with that, let's dive in. So this is a figure that was taken out of some work done in Minnesota. It was a tile drainage study. We're not super interested in that aspect. It was just a nice figure showing early season precipitation patterns relative to crop water use. So crop water use is the solid black line you see here. Precipitation is the tall yellow bars. So you can see that between, preseason and about June, plus or minus a few weeks there, we're getting a fair amount of precipitation with very little crop use. So there is that early season nitrogen loss potential that exists out there. And now let's kind of bring in the nitrogen use by the crop into this picture. So this is from Iowa State. Looking at as you move throughout the growing season here on the x-axis, you can see that the nitrogen uptake increases over time. Let's drop in some different time points here relative to that. So I kind of extended this x-axis into the past, right? So let's look at last fall planting season right about right now, and maybe that V9-ish growth stage. So these are some of the common timing strategies that we consider and that growers like yourselves consider. Looking at fall applications, pre or at plant applications, and then some combination of either in-season side dress or maybe a split between planting and in season, or several in-season split applications. And so really the whole goal here is to manage our nitrogen timing decisions while considering what's the weather been doing, what are the soil processes that are happening, especially in this early season. We know as we progress into the months of June and July that mineralization and nitrification of organic sources of nitrogen in the soil really start to ramp up as well. And then really ultimately we want to make sure we have available nitrogen to the crop when that crop actually needs it. So that just kind of sets the stage for why considering and thinking about an application timing is important. So with that, let's dive right into the first study that I'd like to review with you all today. So we have this was back in 2014 through 2016. We had 49 site years over the course of those 3 years. And what was really, really cool about this study is that every partner in this study followed the same standardized protocol. And that protocol, as it was related to nitrogen, was the same rates were applied at the same timings. And we had 2 different timing strategies that we'll talk about. The first was everything was applied at planting. So we had rates from 0 up to 280 pounds of nitrogen per acre applied at planting in 40-pound increments. And then we had a split set of treatments where we put 40 pounds down at planting and applied the remainder, again, up to a total of 280 pounds at V9, which recognize might be a little late for what we're used to up here in Wisconsin. That's just one of those things that you kind of have to adapt when you've got 8 different states and you're trying to do what's representative across the whole geography. So some of the data that we'll talk about today, we'll look at yield as it relates to rate as well as by timing. So looking at plant versus the split. We'll look at total above ground and uptake, couple different nitrogen use efficiency measurements, as well as post-harvest residual soil nitrate. And we'll look at what implication timing had on all these different things. So to start off with, just set the stage of kind of the whole story and how we did the statistics and all this. This is a pretty standard yield response curve. Most of you have likely seen this more than one time. I'll apologize in advance. Some of these slides are still in SI units. Yeah, we know this is supposed to be 40, 80, 120. Didn't have time to update the figures today. But we're looking at increasing nitrogen rate on the X and of course yield on the Y. Just to bring it into English units a little bit, this is about 95 pounds per acre. And this is about 70 pounds per acre. So those are the economic optimum N rates. So for all 49 sites, for both timings of nitrogen application, we calculated the economic optimum N rate. And knowing that, you know, our recommendation tools that exist out there, be that the MRTN, and in other states, there might be the yield goal approach and some more sophisticated approaches. We know that predicting the actual EONR is difficult at best prior to the season. So we were pretty interested in having maybe a more practical range of N rates to use to compare the two timings and some of these other metrics. So what we ended up doing was calculating the range of nitrogen rates that would have resulted in profitability or return to nitrogen within $1 per acre of the true site EONR. And so that's what these blue and magenta or pink bars represent. So for the at plant, here's the EONR, and this is that range of N rates that were within $1 of profitability per acre. And when we did that for all the sites for both timings, we came up with about a 20 pound per acre mean. So the average across all the sites and timings, you know, the width of this gap here or bar was about 20 pounds of nitrogen per acre. So we'll just kind of say that now. We'll bring that up later as we get a little deeper into this. So we did this 49 times 2. And then now we're going to look at some agronomic, economic, and environmental metrics relative to these site EONRs for both timings. So diving into some of the agronomic measurements that we did. So this is total above ground nitrogen uptake. And I'm just going to take a second to unpack this because there's a lot going on here. So on the x-axis, you'll notice that we have this term called delta N applied. And what this does is this normalizes the data set so that EONR, or that optimum nitrogen rate, is in the middle of this axis across all sites. So on any given site, right here was the perfect N rate to optimize profitable yield. And then on the Y, of course, we have total N uptake at R6, so physiological maturity. Let's talk color coding really quick because this is going to show up on a few subsequent slides. Throughout some of this analysis, we saw that certain clusters of sites were behaving a little bit differently than the majority of the locations that we had. And so to call them out here, so we had some tile drain sites. Those are indicated by orange. We had sites where we documented in-season N loss, a high amount of in-season N loss. That showed up in several different parts of our data set and also in-field observation. Those are the magenta or pink, red, however that's showing up on your end. We also had some sites, 5 of them, that were either non-responsive to nitrogen, or the way the nitrogen response curve statistics looked, the optimum N rate would have been lower than our actual lowest N rate that we applied. So what that means when you boil this all down, if 0 is the perfect N rate here, anything with a positive value represents an over application. So nitrogen that really wasn't needed to optimize yield, and a negative value on these axes represents an under application. So across all sites, we fit a response curve of this delta N applied value to an uptake. And at 0, again, EO&R across all sites between timings, we estimated what total N uptake was. And what you'll see here is that for the at plant time, we had 192. And for the split timing, we had 194. And those were not significantly different than each other. So timing had no effect on N uptake, again, across this enormous data set in geography. So we're just talking about big picture results here. We also looked at a couple of different nitrogen use efficiency parameters. This one is partial factor productivity. It's the easiest one to capture outside of that research setting, right? So it's just bushel, grain yield bushels divided by total N applied. Same x-axis here again, so over applications, under, but at EO&R across all sites, again, no difference in that end use efficiency metric between the timings. Just a second one here, agronomic efficiency. This one is just looking at the bushels of grain from fertilizer. So we had to subtract off the yield from a 0 N check plot to get at just bushels of grain from N divided by total N. And again, no difference in NUE here between timings. Looking at the environmental component of this, so although we didn't directly measure nitrogen loss from the system, what we did do was measure down to 3 foot soil nitrate after grain harvest. And so we're kind of using that as a proxy to see how much N might have leached out during the growing season and how much N is sitting in that profile that could be leached after the growing season. And so again, when you fit these response models, looking at, again, 0 being the perfect N rate, solid line being our at plant time, and our split line, or this dashed line being the split applied N, we actually did see a significant difference in residual soil nitrate between timings. So that the split application, again, on the average across this data set, was resulting in about 20 pounds of nitrogen per acre more being left in that profile from splits over the single at plant. And so one of the biggest takeaways from this analysis is that the rate that you apply is really driving how much N is likely going to be lost. And that's pretty evident. You can see as we start to over apply, these curves start to increase quadratically or pretty quickly here. But when you're applying at rates, under that optimum, it's a pretty static, soil nitrate was very little affected by increasing rates up to the optimum. So rate really drives how much is going to be lost or could potentially be lost. What timing is doing is simply shifting when that N is going to be or could be lost, right? So the plant applications you might say we lost 20 more pounds during the growing season compared to the splits. Or another way of saying that is if you split applied on these trials, there's 20 more pounds that are likely going to be lost after the growing season versus during. And I just want to take a quick moment. Being the conservation outreach specialist, I have to put a plug in for fall planted cover crops. And so, if we're doing split applications and we suspect greater soil nitrate left in that soil profile, can we get a cover crop established in the fall to scavenge some of that nitrate, keep it in that biomass and near the soil surface so that throughout the course of the following growing season, that can mineralize back out and be used by subsequent crops. So just want to get that shameless plug out there. So if we ask ourselves this question, is the economic optimum N rate also an environmental optimum N rate? Let's come back to this 20-pound range of N rates that we said were within $1 per acre profitability of the actual true EONR. So what we did is we took this data set over here, the one with all the cool colors, and we move it directly to the right here. What we did was we binned these delta N categories into 20, call it 20 pound per acre bins. And so, for example, this one here in the middle, this is 10 pounds of N under EONR, all the way up to rates that are 10 pounds over EONR. So that just kind of gives you an idea of what this x-axis means here. So we're saying if we could predict EONR within 20 pounds, 10 pounds on either side, what would this tell us? So the first key takeaway is that using residual soil nitrate as that kind of proxy or indirect measure of environmental impact, you'll notice here the soil nitrate in those rates right around EONR were no different than where we under applied by over 90 pounds per acre. And so generally that's where we didn't apply N on these sites. So, you know, there's no difference in soil nitrate there. When you step up one notch here and you go up to 30 pounds over the true optimum N rate, those nitrate levels are the same as if we under applied by up to 50 or 70 pounds, all the way up to 70 pounds. So really what this tells us is that future nitrogen rate recommendation tools need to be able to predict and recommend rates that are within, you know, no more than 30 pounds over that particular field's actual optimum nitrogen rate. Once you apply over 30, you start to see soil nitrate accumulating at significantly higher rates. So then kind of to wrap up this regional study looking at timing and rates. So let's look at EONR across all these sites. And so what this figure does is it's taking the optimum N rate for the at plant applied N, and we're subtracting off the EONR from the split applied N. So a positive value on the y-axis means that it took more nitrogen when we applied it at planting. It took more nitrogen to optimize grain yield and profitability than if we split applied. And vice versa, if you have a negative value, split applications were advantageous over single at plants. And so you can see there's a lot of ups and downs on this chart. Boiling it down on the study average, we had about a 9 pound per acre advantage of split applications with a 2 bushel per acre yield advantage. You can see there's a few data points in either direction that are likely having a lot of weight on those averages, but that is what it is. And then down here just kind of breaks down, you know, where did we need more or less N for at plant splits? And when we say that the two timings resulted in an equal EONR, what that meant was those rates, those optimum rates between timings were within 20 pounds of each other. That's what we used as kind of our practical difference. So, you know, about a third, a little better than a third of the sites, they were the same. About a third, they were at plant took more N, and the rest at plant was actually beneficial. Looking at return to N, cut to the chase here. Again, study average, 323 pounds of the acre for at plant and $343 for split. Now, this is not considering additional application costs of making that second application for the split, so keep that in mind. But I do want to highlight these sites that had a lot of nitrogen loss from that early applied nitrogen. So again, this is showing us a huge economic advantage of those split applications. And what these purple sites all are either very heavy clay soils that are very to poorly drained, or they're very sandy soils that are excessively drained. And so we know based on the precipitation data that we collected that these are sites where we experienced either high denitrification losses or significant leaching losses. So in a nutshell from this study, right, they're on the average across sites, the timings are resulting in very similar yield and optimum N rates and profitability. but we do need to be cognizant to call out, these very poorly drained soils that are going to experience denitrification losses early in the season. And our coarse textured soils, we can see a very clear picture that split applications are certainly advantageous. Let's pull in a little bit of Wisconsin specific research. I know Dr. Carrie Lebowski presented some of this work back in 2020 in a previous Badger Crop Connect. This particular study has a very similar storyline to it. We're just going to focus on 3 different timing strategies, and this will be much shorter. So we had all the unapplied pre-plant, all the N applied as a side dress around V6, and then a split application again with 40 at planting and the remainder at side dress. Here's some other background information that we don't need to spend a lot of time on, but again, using Lancaster, Ag Research Station, and Marshfield. So we have another well-drained soil and a somewhat poorly drained soil. So let's keep that in mind as we take a look at yield. So at Lancaster, let's take a look. So the red represents N-applied pre-plant. Orange triangle represents all the N-applied in the season at V6. And the yellow diamond is 40 pounds at planting and the rest at V6. You can see here there was no effective timing on yield or optimum N rates. Fast forward to Marshfield, and there's a pretty different story to be told. All the N that was applied at planting definitely resulted in lower yields across the whole range of N rates. Putting 40 pounds out at planting and the rest at side dress helped a little bit here at the 80-pound mark, and then certainly quite a bit at these higher rates. And waiting until V6 to put all of the N on actually yielded, the highest or very similar to the split application. So again, on these poorly drained soils where we know spring field conditions are very wet, lots of denitrification losses are likely to occur, we can see here that split or in-season applications are advantageous. And just to wrap up, here's the dollars of this whole operation. So blue bar is Lancaster, that well-drained soil. Green is Marshfield, the poorly drained soil. You can see quite a difference in profitability at planting versus these other timings. So at Lancaster, no difference in profitability. Didn't matter, just get the N out there. At Marshfield, again, the split or single in season definitely paid the bills a lot better than the N applied at planting. Last little bit of data we'll share is from Mr. Kevin Shelley from South Central Wisconsin. This is some older data, and it's cool to see that we're all still looking at nitrogen rate and timing and trying to figure it out. But these 3 data sets all had a very good story to tell, focusing on really drainage class and texture, right? So on Kevin's trial here, in 1 year at Arlington, they were on a poorly drained soil. The next year, a well-drained soil. The treatments, they had a split application, a little more than half at planting, the rest at side dress, versus all the N at planting. Let's look over to yield. You can see a very clear yield advantage to doing that split application, and also a return to that N. On the well-drained soil the next year, there was no difference in yield. And the only difference, this $5 per acre difference here, is just accounting for the second application cost of that split application. So same story, poorly drained soils, split applications are pretty advantageous. So which time is better? Soil type and precipitation are the key drivers. So just to reiterate, sandy soils with a high probability of leaching, split application, certainly the way to go. Fine textured, poorly drained, split applications are the way to go. Aside from that, on medium and fine textured, well-drained soils, really just get the nitrogen out there, get a sufficient amount of nitrogen out there. And much of the data that we've looked at today, and much of the data we didn't talk about today, tells a very similar story. of course, we can't predict the weather. So if you make a decision all at plant or all at V6 and you get a 3 or 4 inch rain, you might see some N loss. We can't predict that. On the average, just get the nitrogen out there. And what's really cool about that is on these well-drained soils, it gives you a little bit of flexibility. So if let's say at planting time, time is a restraint for you. You have a lot going on, or the co-op can't get out with the fertilizer, what have you. You can bump it to in season, right? If you have the right equipment, if the co-op or your neighbor, whoever has the right equipment to go in over the top of, V5, V6 corn, you can certainly bump it to later in the season. So it just gives you some flexibility on these well-drained soils to just pick which one works best. But do just keep in mind to consider the additional application costs if you're doing a split where you're applying and more than one time. And to wrap up, key takeaways from the data we looked at today. So profitable production can result in low risk of N loss, right? Where we showed using that residual soil nitrate as the indicator of N loss. If we're applying N rates within, 25 to 30 pounds of EONR, not going over EONR by that much, we're doing a pretty good job from an environmental standpoint. And again, the rate is really going to drive how much we're losing, and timing is simply just affecting when we're losing it. Consider your soil texture and drainage when you're making your application time decisions, and ultimately do some on-farm research. And we have a ton of extension educators that all are very motivated and excited about on-farm research, but doing rate trials and timing trials on your own farm, on your own soils, in your local, weather environment can really help you dial in what's working best in your area, on your operation. Just really wanted to show some bigger data sets that kind of steer us in the direction of it's really up to texture and drainage, and of course predicting the weather. So just want to acknowledge the folks that help contribute to these data. So that Pioneer Regional team, Carrie Lebowski for some data, Kevin Shelley, and Dr. Matt Ruark for reviewing this prior to today's talk. So with that, thank you, and I will be sticking around afterwards if there's any questions.